Okay, exponential models, page 17 and 18. Um, Page 99 reading. How much does the radioactive substance decay every year? So in the book, they talk about some kind of radioactive material, and when you have a radioactive material, um, the only way to make it less radioactive is to wait. The longer you wait, the less radioactive it gets, and the amount that it becomes less radioactive is exponential. Okay, so it will go down kind of like in this shape. Okay, so and what does this shape look like in terms of an equation? Well, they say that the radioactive substance decays every year by 5%. Okay, now, if you have like 100 and it reduces by 5%, then you subtract 5 and then you get 95, right? And then you subtract 5%, it's going to be a little bit less than 5, and then you get the next number, etc. Okay? But how do you multiply a number times 100 and get 95? Well, let's see. What number do you multiply by 100 to get 95? The multiplier would be 95, 0.95. So 95% or 0.95. So to reduce the number by 5% each year, you multiply by 0.95 each year. So, for example, if you want to get the weight of the radioactive substance in the first year, you take the beginning weight and you're going to multiply it times 0.95. So what is that in terms of numbers? It would be 20 because that's the beginning weight times 0.95. What about the second year? So the second year, you take the first year's weight and you multiply it times 0.95. And what about the third year? The third year, you take the second year's weight and you multiply it times 0.95. Okay? So, and then what does that look like in terms of numbers? Let's see. So the second year would be 20, which is the beginning amount, times 0.95 times 0.95, which would be equal to 20 times 0.95 squared. The third year would be 20 times 0.95 times 0.95 times 0.95, which would be 20 times 0.95 cubed. So what about in the nth year? Okay, the nth year would be some year in the future. We don't know exactly how many. They want a general formula for you to calculate the nth year once you figure out what n is. So you can see the pattern here. In year 3, the weight is equal to something, something, something cubed. In year 2, the weight is equal to something, something squared. So in year n, the number of times you multiply 0.95 would be n. Okay, so this is the general formula to find out how much radioactive material is left in after n years. Okay. So that's how the decay works. You can see that it's similar to what we did before, where we did exponential growth of a population. So remember that we had the multiplier in that case was a number that's bigger than 1. When we do decay, we have a multiplier that's less than 1. So multipliers less than 1 gradually makes the amount get smaller each year. And if you have a multiplier above 1, then it becomes a little bit bigger each year. Okay, so let's do a few of these problems. First, number 1. The weight of a radioactive substance T years after being set aside is given by weight equals 250 times 0.998 T grams. So you can see that since the multiplier, 0.998, is a little bit less than 1, gradually it's going to get smaller and smaller. So how much radioactive substance was initially set aside? I don't know. Well, initially set aside means T equals 0, right? Beginning of time. If I put T equals 0 in that equation, I'm going to get 250 times 0.998 to the 0. Wait a second, 0.998 to the 0, I don't even need a calculator for that. That's equal to 1, right? So the initial amount of the radioactive substance is just the initial constant there that's multiplied times the whole thing. Okay, and by now you're starting to get that, right? They've asked you that question many times. You've done the investigation. You're coming to realize that whatever number you have multiplied in front of the exponent is going to be the initial value. Determine the weight of the substance after 400 years. Okay, so that would mean we put in 400 for t there. So, like for example, you would have 250 times 0.998 times 400. Okay, and we'll do that in the calculator. We'll do that on the calculator in a second. Next one would be 250 times 0.998 times, or to the 800th power. Okay. All right. Now let's look at two different ways to do that on the calculator. First way I'm going to show you is just using the regular screen. So 250 times 0.998 to the 400th power. We'll see what that is. It's 112.24, so we'll say that's 112. What about to the 800th power? So we can type that again, and we're just going to back up here. We're going to replace the 4 with an 8. Okay, and it's 50.39. It's 50.4, right? And you can see that since the multiplier is a little bit less than 1, the number is getting smaller every time. What about for 1200? Okay, 22.6. Okay, so now I'm going to show you another way to do it. And if you don't understand this right now, that's okay. We're going to be doing several other examples like this throughout the math course. You're going to eventually understand. The other way we can do it is we can put the equation inside the y equals screen. It's the function screen. And I'm going to put the equation here, and I'm just going to change t to x. So I'll put 250 times 0.998, and then I'm going to put x. Okay? X. Okay, and then I'm going to, I could graph it, but actually what I'm interested in seeing is seeing the data. So you can see here that this already gives you the answer to the initial value. It gives you 250, and then it gives you the value for many others. Now, for example, if I want to see what the y value is for t equals 400, I could do that just by going down here, but that would take a long time, right? Because I would have to do that 400 times. So what I'm going to do is I'm going to change the step size. I'm going to change the step size to 400, because if I change the step size to 400, then in the x values I would see 0, 400, 800, 1200, which is exactly what I want here. So I'm going to change the step size by pressing plus. Plus. And then it gives me the opportunity to change the step size. I'm going to change the step size to 400. So now you can see instantaneously I got all the values I wanted. X equals 400, the value for y is 112. X equals 800, the value is 50.4. And for 1200, the value is 22.6. So you can see the calculator can calculate all these values all in one shot. You don't have to keep typing in the same equation again. Sketch the graph of WT for t is greater than or equal to using A and B only. Okay, so you only have a few points. Your points are 0, 250, 400, 112, 800, 50, and 1200, 22. So let's use this paper here and graph that out. So we got year 0. Let's see, we got about, I think we can put like 100 for each one. So 0, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,100, 1,200. Okay. Let's see. So for 400, it would be 112. For 0, it would be 250. So let's mark 250 here. We'll use 100, 200, 250. So this will be 250. And then the next point is going to be 400, comma 112. So 112 is right there. And 800, comma 50. And 1200, comma 22. Okay, and then we're going to graph. Okay. All right. So that is the graph of the function w. Use your graph or graphics calculator to find out how long it takes for the substance to decay to 125 grams. Well, we can kind of estimate that by looking here. This is 100 here, right? This is 200. So 125 is around here, right? Maybe about there. That would be about, I don't know, 350 or something. So from the graph, you might estimate 350. Now, the calculator would be even better to estimate that. Let's, instead of changing the step size to 400, let's change the step size to a 100, and then we'll get a little bit better precision. Now let's see, when do we get to 125? Well, it looks like it's somewhere between 137 and 112, so it'd be maybe it'd be 350 looking at this. We can get even better resolution by doing this again. We could put 200, I'm sorry, 50. And then you could see that, let's see, we'll go to 350. Ooh, that's very close, isn't it? So yeah, 350 is very close. Okay. So that's it for number 1.